Section 6.9 is about the momentum paradox, as I like to call it. The momentum paradox. 6.9. So let's suppose we have a person standing on the ground like so, and they are standing there, and very clearly their momentum is zero. They're just standing stationary. Their velocity is zero, so their momentum is zero. Now they're standing there and they decide they want to go somewhere. So they start to move. And now they have a velocity that is not zero. It's a non-zero velocity. And they're moving in this direction. Well, now their momentum is not equal to zero. So it seems that we just have a creation of, or an increase in momentum. And so this seems to violate the law of conservation of momentum. We have a person, they have no momentum, and now all of a sudden they do have momentum. Well, let us consider this a little differently now. Let us suppose that we have the person who's standing here, and they're standing there on a skateboard, and their velocity is zero, and their momentum is zero. And when they step forward, they will have, let's say they have a velocity of 1 meters per second. The skateboard will launch in the other direction as they step off that skateboard. Now, if the person has a mass of 100 kilograms and the mass of the skateboard is 1 kilogram, well, what we have in that situation is an explosion where the initial momentum must equal the final momentum. Initially, the momentum is zero, and the momentum after would be the momentum of the person plus the momentum of the skateboard. And so the momentum of the person must be equal and opposite to the momentum of the skateboard. The mass of the person is 100 and their velocity is 1, so they have a momentum of 100. And the momentum of the skateboard is equal to its mass of 1 times its velocity of the skateboard. So clearly then we can see that the velocity of the skateboard would be 100. The person's mass is 100 times that of the skateboard, so the skateboard's velocity is 100 times that of the person. And in that situation then, we see that the momentum is conserved. We have positive momentum for the person and negative momentum of the person. They still add up to zero. So the momentum of the system remains the same. So it first seems like a paradox of a person standing on the ground. We still yet to have resolved that, but by looking at a skateboard, we can see that difference. Now, let's suppose we have a John boat, and a person is standing on that John boat, the same person, 100 kilograms, and the John boat is 100 kilograms, and they are both at rest, and so we see the initial momentum is zero, and then afterward, the person steps off at 1 meter per second, and until they hit the water surface, they're moving forward at 1 meter per second. So there's the momentum of the person and the momentum of the John boat. Momentum of the person must be equal and opposite to the momentum of the John boat. So we have a 100 kilogram person times its velocity of -1. And we have the mass of the John boat, which is 100, times its velocity. Well, clearly then, if that's the case, we can see that the velocity of the John boat must be a negative of -1 or +1. So we have, in this case, equal masses, and we have equal and opposite velocities. And so momentum is conserved. Now we go on to a cruise ship. We have a person standing on the front of the boat, and they have a mass of 100 kilograms, and they're standing there with their arms outstretched, and they say, "I'm the king of the world!" And they step off that cruise ship with a speed of 1 meter per second. Let's say that's negative. We have positive velocity and negative velocity like so. Well, we know then, and it's hard to see and hard to imagine, but the boat, the cruise ship, will move backwards in the opposite direction. So we have P0 is P, and we have a momentum of the system is zero beforehand, and afterward we have the momentum of the cruise ship and the momentum of the person. So the momentum of the cruise ship must be equal and opposite to the momentum of the person. So we have the mass of the cruise ship, which is 60,000 tons. and there is about 1,000 kilograms per ton. So we're left then with about 60 million kilograms. So we have the mass of the cruise ship times the velocity of the cruise ship, and the mass of the person and the velocity of the person. Well, the mass of the cruise ship is 60 million. 60 million. 60 times 10 to the 6th times its velocity, and the mass of the person is 100 and the velocity is 1. So then we can see that the velocity of the cruise ship is about 60 times 10 to the 4th. Whoops, 1 over 60 to the 4 times 10 to the 4th. So 1 over 60,000. 1 over 60,000 is meters per second will be its velocity. So we can see then that in this case, we have the momentum of the system, which is the person and the cruise ship. In the middle case, we have the person and the John boat, and we have the person and the skateboard. Well, how do we resolve the momentum paradox of a person standing on the ground and they step forward and seemingly create momentum? Well, I imagine at this point you have your answer, that the system is the person and the earth. The person gains momentum in this direction, and the earth will gain momentum in the opposite direction. So whenever we seem to have a paradox, it may be that we simply have not defined our system properly. And so adjusting to systems thinking can be a challenging shift of our minds, but it can resolve what are seemingly paradoxes. In our next installment, we are going to look at examples of momentum in action.